So a power 100, a power 1000. In Markov chains, we wanted to find out a power infinity. We use diagonalization in those kind of cases because even a power infinity, we will prove in that case that the limit still works. Xa x inverse when multiplied by xa x inverse gives x a square x inverse. And multiplication is very good in general because the diagonal matrix is sandwiched between a matrix and its inverse. And if you were to multiply that by the same matrix, the inverse and the matrix will just combine it and go away. And you would still get something sandwiched between the matrix and its inverse. So, one more application would be in J kind of questions where they would give the matrix some special matrix A, and they would ask what is the value of A about 100, A about 50, and you would need to find a pattern. You would find A square, A cube. Well, you don't really need to find a pattern. Finding a pattern might not be obvious and difficult questions. What you would rather do is you would find the eigenvector matrix, you diagonalize it, then you would find the power. You raise it to the power, and in every case, in every single problem of that kind, it can be done very easily with this method. So if x a equals x lambda x inverse, we have a power n equals x lambda power n x inverse. Lambda power n is simply the every diagonal element raised to the power n. Lambda power n is very easy to find. You sandwich that between x and x inverse. Instead of having to multiply n times, you do matrix multiplication only 2 times. X with lambda power n, the product with x inverse. You have an extremely big reduction because in computer programs, you need to do a lot more operations to multiply matrices like A, while taking the power is very easy as compared to exponentiating a matrix with itself. And after all, we are doing a constant number of matrix multiplications, so we're turning like n matrix multiplications into a constant, which is an extremely good reduction. So yeah, that's how we applied. Now, can we diagonalize every matrix? Is every matrix diagonalizable? The answer to that question is no, because, well, because there are a lot of reasons, but it might turn out to be that the eigenvectors and eigenvalues themselves cannot, in a way, describe the matrix completely, because we know that some matrices can share eigenvectors, some matrices can share eigenvalues. The eigenvalues themselves might not be unique. If you have x minus 1 the whole square, 1 comma 1 is an eigenvalue. Well, when do the eigenvalues characterize a matrix? Eigenvalues characterize a matrix when they are unique. So if you have n unique eigenvalues for an n cross n matrix, you have n different eigenvectors, and that is when you can diagonalize a matrix. If you have an n cross n matrix, you need n eigenvalues and n eigenvectors. Now, if you have an eigenvalues, interestingly, it is guaranteed that you actually do get n eigenvectors. And the way you prove that, I won't go into too much into the details of the proof, but essentially, the way you prove that is by saying different eigenvalues correspond to linearly independent eigenvectors. They're not just different, remember. I mean, the vector 1, 1 is different from 2, 2, but obviously it's just 2, 1, 1 with a scaling factor, right? So different eigenvalues correspond to different linearly independent eigenvectors. And it's not just they're pairwise linearly independent, they're entirely linearly independent. It's not just you take any two and it's not the one is not the scaling of another. If you have 1, 2 and 1, 1, 2, 3 will never be an eigenvector if the eigenvalues are different, for example. The proof of that is quite deep, I think. I don't think we can cover it in a short time. So for now, just take it as a result. Different eigenvalues correspond to different and linearly independent eigenvectors. Keep that as a result for now. And let's move on. Right. So next, for a example, we'll take the example of Markov chains because Markov chains is I mean, we use these kind of things excessively in Markov chains, and in a way, this technique was we could say like these two were invented during the same time. These techniques. So Markov chains made extensive use of this. Markov himself. Now we have a Markov matrix A equals 0.8, 0.3, 0.2, 0.7, and we have lambda 1 equals 1, lambda 2 equals 0.5. Note that lambda 1, lambda 2 are distinct, so the eigenvectors must be linearly independent. Here, there can be a maximum of two vectors, eigenvectors, and we have the two eigenvalues different correspond to two linearly independent eigenvectors. So we want to diagonalize this matrix and raise it to the power n, and eventually take the limit of n tends to infinity. What we do here is we have 1.5. We get the eigenvalues corresponding to them as 0.6, 0.4, and 1 minus 1. In the case of a 2 cross 2 matrix, it's quite easy to take the inverse. And in this case, I think the determinant of A, I mean, the way you do it is you flip the diagonal elements and you take the negative of the other two elements, and then you multiply it by the adjoint. That's how you do it. I think you can look it up if you don't know, but uh, it is pretty trivial. So the way they finally diagonalize it themselves, and you should probably work out this example later. Look at the slides, work it out. And you have this random looking matrix is something times something. These two are random times a diagonal matrix. This diagonal matrix is what we want for multiplication, right? If we take a square, a cube, a power n or something, it's still two diagonal random matrices here times each element raised to the power k. Each diagonal element raised to the power k. Now we want the original problem posed by Markov. We want to find the limit of k tends to infinity. We have a 1 here, so that remains a 1. And 0.5, so 0.5 becomes 0.25. You get the decreasing, monotonically decreasing sequence, which is bounded below by 0. So we have a limit, and it just gets smaller, right? Any number, any epsilon you talk about, you can always find 0.5 to the power k, some k such that k is less than epsilon. That's how we prove that the limit is 0. I mean, if it wasn't obvious enough already. So you get a very good matrix, 1, 0, 0, 0. And after multiplying, you get this. Now, if you had just sat down and multiplied A with itself, you would have probably taken a lot more time, right? I think this example itself demonstrates the utility of Markov chains. Now, another application. So, when does A power k as k tending to infinity become a zero matrix? So, think about it. What conditions do I have on A power k? I wanted to think about it in terms of this diagonalization process. So, yeah, okay. Okay, in the before slide, A was given as x lambda x inverse, and then lambda was given as x inverse. Yes. Yeah, that is indeed correct. So you have this equation, right? So, oh wait, okay, I'm sorry. Lambda will turn out to be x inverse A times x. The way you derive this is you start with this equation and you pre-multiply by x inverse, you post-multiply by x. So x inverse ax equals lambda. Right, right. Thanks for pointing it out. But yeah, it's a matrix times A times its inverse. So yeah. Oh, by the way, I might have forgotten to mention something. So we will talk about similar matrices in the future. And what is interesting is that similar matrices share, they are a class of matrices which share very good properties with each other. And similarity transcends diagonalizability. That's how you build upon to the next step. The Jordan canonical form, I'm hyping it up a lot because it's extremely powerful. That's how you build upon it. And so the basic definition of similarity, you say matrices A and B are similar if A can be written as y b y inverse, or rather, if two matrices A and B are diagonalizable and you call them to be similar, what you do is they share the same diagonal eigenvector matrix. So eigenvalue matrix. You one example would be you take some 2 cross 2 matrix, you get two eigenvalues, right? You multiply them with two different eigenvectors, you get two different matrices. Those two matrices would be similar. I think we have some slides covering those. Anyways, I just want to give a trailer for that. So I guess the doubt is cleared. Yeah, okay. Got it. Fine. Right. So when does a power k as k tending to infinity become a zero matrix? We should think about this. In order to think about this, let's look at the previous example. So what did we have? We started with a random looking matrix. We diagonalized it. Now, before that, let's do this question for diagonalizable matrices, because for non-diagonalizable matrices, we cannot say anything for sure without going into higher theory. Right. So we diagonalize it as x lambda x inverse. A power n would simply be x lambda power n x inverse. Now, when would that become zero? That would become zero. X times x inverse is 1. Right? So, I mean, in case lambda becomes some constant times identity or something, it's not useful. In fact, if lambda were anything other than zero matrix, you would never get it to be, you would never get a power n to be zero at all. So, when does lambda power n become zero? You have to look at this for that. So, lambda power n, every diagonal matrix is raised to the power n. Here, power k, it's given here. And it becomes zero when every diagonal element is less than 1. 1 power k does not become zero. Anything greater than 1 to the power k as k tending to tends to infinity blows up. And anything lesser than 1, so the magnitude of it must be lesser than 1. It just shrinks down to 0. A similar approach can be used for complex numbers, but you have to be a tad more careful in that because the direction keeps changing. But in general, I think you can claim that if the modulus of the complex number is less than 1, you can, if you exponentiate that enough, you will end up like going down to 0. So what are the diagonal entries themselves? The diagonal entries themselves are the eigenvalues, right? So each eigenvalue must be less than 1 or have a magnitude less than 1 in order for a power k to be 0 as k tends to infinity. Now, I think this is a very cool result because a power k, you can have like random elements and you do two operations on it, find the eigenvectors, eigenvalues. This is one way in which eigenvalues, like this is the true power of eigenvalues. They characterize the matrix. Any property you have of a diagonalizable matrix can eventually be boiled down to some property of the eigenvectors or the eigenvalues. And in many cases, they actually do help in simplifying the calculation. Right. So similar matrices. As I was talking about, matrices of the form C equals XA X inverse. These matrices need not be diagonalizable. In case they are diagonalizable, they will share the same eigenvalues. Even if they're not diagonalizable, it turns out to be a fact that they share the same eigenvalues. One more property is that they will share the same trace and the same determinant, right? So the same determinant, how do you prove that? You take determinant on both sides, mod C equals mod x a x inverse, and mod x inverse is 1 by mod x, so those two cancel, mod C equals mod a. Trace, the way you prove that is a bit of brute force, but essentially x inverse will contain, will still be a diagonal, okay. X inverse, well, the way you prove same trace is you take a random x, you take an arbitrary x inverse, and you multiply it, I guess. There might be a more elegant proof. In the case of diagonal matrices, there is obviously a more elegant proof because they share the same eigenvalues, the eigenvalue matrix, and different eigenvectors. So from that you derive it basically. Now, what is more interesting going on is what they represent geometrically. So now this is slightly subtle to catch, right? If a matrix is a linear transform, right? Now, the way you look at a linear transform, the way you characterize a linear transform is you take a basis. So if I'm looking at the 3D space and I'm looking at some matrix transform A on the space, what I essentially need to do is look at where 1, 0, 0 gets mapped to, 0, 1, 0 gets mapped to, 0, 0, 1 gets mapped to. Because every other vector can be written as a combination of these three vectors. In essence, if I knew where these three vectors were getting mapped to, I would have knowledge of the entire linear transformation. Now, very interestingly, it turns out if I do the same exact transformation to these three vectors, but not to these three vectors, I choose another set of three orthogonal vectors that form a basis. That matrix would be similar to A. Now, A is a transformation 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, I take three different vectors. I don't think they necessarily need to be orthogonal, so that needs to be checked. And I do the exact same transformation. So, if I want to scale everything by something, these three vectors, I scale it by the same factor. It would turn out that C is similar to A. If I were to shift A, say right, this I would say shift it up or something. And this also I were to shift it up or something. That would give me A. Let me take three other vectors, 1, 3, 2, and two more perpendicular vectors. I do the same thing. I shift this vector right as it along this vector along where this vector originally was, and this vector along where this originally was. I get a different transformation, obviously. But if you notice, if I relabel all the points, it would in a way be the same. I mean, it's an isomorphic transformation in a way because I'm just relabeling every point as every other point. So that relabeling process is taken care of by the x inverse in a way. I mean, and that is another way to explain the fact why the determinant is the same. Because determinant would be in a three-dimensional thing, it would be a volume formed by these. And if you had to transpose it, the determinant would basically explain how the volume changed. And no matter how I transform it, the volume of space would not change because I could take any two sets of vectors as a basis and perform the same transformation, and whatever was initially there would still be there, right? Because in a way, it's just relabeling of every point. So yeah, that is another way to explain why they have the same determinant. But geometrically, it's very interesting. They explain isomorphic transformations. Right. Okay. Going on. Now, I hope all of you know Fibonacci numbers and fine. Fibonacci numbers, you start with 0, 1. The next element is, so you start with 0, then 1, then you add them. 0 plus 1 is 1. Then 1 plus 1 is 2. 2 plus 1 is 3. 2 plus 3 is 5. Just go on. And you may have figured out that, so you may have studied that there is a closed form for the Fibonacci numbers. It's some root 5 minus 1 by 2 the whole power n or something. That's the way you generate them. You can find out any Fibonacci number that way, or you could use the recursive way. An plus 1 equals an plus an minus 1. But these involve a lot of operations, and the first method I said root 5 minus 1 by 2 plus root something power n plus root 5 plus 1 by 2. That involves less operations indeed, but there is a easier way to generate that, and there's an interesting way using matrices to derive that. So let's look at that. So Right. Let me look at the vector space where every vector is of the form fk plus 1 fk. Can I do addition on this vector space? Yes. Can I do scalar multiplication on this? Well, no. So this exactly does not form a vector space. So, but it is part of a vector space of all. Well, this does not form a vector space, obviously, but if you consider all the vectors of the form of dimension 2, like a comma b, this forms some kind of a subset of that vector space. So we can consider everything of this one to be a vector. Now, every vector of this does not form a vector space, but that does not stop the fact that this is a vector of some other space. And we will look at special vectors of this kind. Now, we want to convert UK to UK plus 1, right? And we want to convert that with a matrix. Now, for a Fibonacci sequence, it does not depend on any constant. UK plus 1 only depends on, okay, the n plus 1th term of the Fibonacci sequence only depends on the nth term and the n minus 1th term. So we have nth term and n minus 1th term in UK. So UK plus 1 ought to only depend on UK. So there ought to be some matrix transformation transforming UK to UK plus 1. So we write down two linear equations, and the thing is they are linearly independent, so that further reinforces the idea that there must be a matrix transformation because it's just addition, right? You don't take square or some random thing. So the rule is fk plus 2 is fk plus 1 plus fk, and fk plus 1 is fk plus 1. So you can generate a matrix from this. If you try out this matrix 1 1 1 0, it works. So UK plus 1 is this thing times UK, and U0 is 0 0, and U1 is sorry, FK is 0, F0 is 0, F1 is 1. So U1 is basically, so U0 is basically 1 0. Now, if I were to repeatedly transform 1 0, the vector 1 0 under this matrix, I will generate every Fibonacci number. What is repeated application of a transformation? It is composition in the functional domain, and it is multiplication in the vector in the matrix domain. So I want to multiply the matrix repeatedly, and that is where diagonalization comes in. You want to multiply something repeatedly with itself. You want to take the power of something. You want to multiply two similar matrices. You go to diagonalization. Diagonalization will surely help you. So in order to diagonalize, we want to find the eigen values of this matrix, and the eigenvalue turns out to be 1 plus root 5 by 2 and 1 minus root 5 by 2 with the quadratic formula. Right. You basically do 1 minus lambda, 0 minus lambda. So 1 minus lambda times lambda minus 1 equals 0, which simplifies to this equation, and this gives the values. And right, so you now have okay, you want to repeatedly multiply this a lot of times. So you also find the eigenvectors corresponding to each of these eigenvalues. Now I write 1 1 1 0 equals some matrix times the diagonal matrix times something inverse. And I want to apply the transformation a lot of times. So now I have some matrix times every diagonal element, the whole raised to the power k, times its inverse. And that will turn out to give you this, which can be derived, but I won't be covering the derivation because it's just arithmetic after a point. And this turns out to be the general form of the Fibonacci sequence, where x1 is 1 and 0. Now, forget Fibonacci sequence, but any sequence which can be generated. You can start with y0, 1. You could start with, say, 1, 3, for example. 1, 3, 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, and so on. Or you could do some other operation, like you could do 2 times 0 plus 1 is 1, and then 2 times 1 plus 1 is 3. You multiply the first element by 2, second element by 1. as long as it is any sequence where you do a linear transformation of a particular number of elements to generate the next element. Or in other words, it is kind of a causal system. The previous elements linearly cause the future outcomes. It is a linear causal system. You can always represent that by a matrix transformation. You can diagonalize it and you can describe that in complete detail. It is that any question related to that can be solved. So yeah, what about matrices that cannot be diagonalized? Uh, Now this is where the intro to Jordan canonical form should be, but I don't think we have enough time to explain Jordan canonical form. But what it basically is you have the diagonal matrix still, but you also have in the diagonal above it, if it's a square, you have a lot of diagonals like this thing. Now, in the diagonal above the main diagonal of the diagonal matrix, you have some elements, and in the diagonal below also you have some elements. And you convert that in some special way. And matrices like these are said to be Jordan canonical. And even if a matrix is non-invertible or it doesn't have enough eigenvalues or something, the Jordan canonical form will still exist. And that form has a lot of properties. And that is like extremely important. Right. So next, geometric multiplicity and algebraic multiplicity. Now, multiplicity, multiple, geometric multiplicity, something geometric that is multiple. We learned about eigenvectors and eigenvalues. Eigenvectors is geometric, eigenvalues is algebraic. Algebraic multiplicity, the number of repeated eigenvalues. Geometric multiplicity, the number of repeated eigenvectors. If the geometric multiplicity or the algebraic multiplicity is greater than 1, then you run into problems. Because diagonalization might not happen and enough eigenvectors may not be generated depending on the matrix. Stuff like that could happen. So these two terms are extremely important. I've covered what they are. What they will be used for, you will see in the future. Right. Okay. So we've talked about eigenvectors, eigenvalues. We've talked about repeated multiplication. We talked about Jordan canonical form. We talked about diagonalization. Let's talk about a different topic. Let's forget all of this. Let's go into calculus. Let's talk about differential equations. Can matrices be used in differential equations? This is like an extremely interesting topic, which you will cover, which people will cover in the future. But let me just give you an intro, like a trailer of what is to come, if I may. Right. So differential equations. First order differential equations in two variables. dy by dx is something, something, something of x. These kind of equations. Right. Now, what is the solution to this equation? Du by dt equals lambda u. This is actually very easy because you take the dt to the other side, you take the u down. Du by u equals lambda dt, you integrate both sides, ln u equals lambda t plus c. And you remove the ln, so u of t equals c e power t. Another way you could think about it is basically du by dt equals lambda u. I think there should be a lambda t here. Yeah, I think it should be c e power lambda t. So if you think about the function e power lambda x, you get the same function multiplied by a constant. And any constant multiplied by an exponential function behave the same way. So that is the most general solution to the first order differential equation. It is of degree 1, so it needs to have one unknown, and c is the unknown. So we've exhausted everything. Right. We know all of this. What about d u bar by dt equals a u bar? So what is different from this? Right. You have a u, you have a u, you have a lambda, you have an a. Well, u is a vector now. It's not a number anymore. This vector itself is time changing. Like you have a vector moving in time in the three-dimensional space, for example. And A is a matrix. you want to transform the initial vector, which moves with time, with its rate of change. You want to correlate this vector with a vector that denotes how this vector is changing. It is, I mean, it is a larger frontier now because we are describing a lot more things. We're not talking about how only one number changes. We're talking about how an entire vector changes. And for that, we need a matrix. So, right, what could be a solution to this? E power a matrix does not make sense, but let's not go to that. I mean, we might want to define that later, but that doesn't really, we don't know anything about it now. Let's choose some vector u bar equals e power lambda t times x bar. And yeah, we take x bar equals a constant, and you x bar is a constant vector basically. If you say 1 0 2 3 2 comma 3 or something, e power lambda t is where all the time varyingness comes. Lambda could be a complex number, obviously. It could be a rotating vector. It could be a scaling vector. Anything that behaves exponentially. If I want to differentiate this, I would basically get lambda e power lambda tx and du bar by dt. What is a times u? Now, the way I choose lambda is that lambda is an eigenvalue and a is an eigenvector. Right, it is a very special vector. So I have a times x equals lambda times x. U bar by dt is lambda times e power lambda t times x bar, which is u bar, lambda u bar. Because u bar is an eigenvector of a u bar is lambda u bar. So I hope everything is clear in this. Do you now observe that ax bar here is lambda x bar, and so these two are equal, and thus it satisfies this differential equation. So one solution to this differential equation is, and it will turn out that this is the only solution, is u bar equals e power lambda t x bar. You take a vector, the variance of the vector, all the varyingness, time varying properties comes from the e power lambda t. So it could be a rotating vector, or it could be rotating as a complex line. You could take the real projection of it. It could be scaling, it could grow real big, it could grow really small. It could do both, it could do a lot of things. All of that comes from this. It can be described by this differential equation, and every solution to this differential equation is a vector of this form. Now I haven't proven the last point which I said, but it will turn out to be true, and the proof is quite more involved. So let's wait for the next session, right? Okay, so now what if we have multiple eigenvectors? We have multiple solutions. So what is the most general solution to this? We still have a first degree equation, but now we have a lot of equations. So now we expect a lot of unknowns. We expect if we can write n different eigenvectors, we expect n different unknowns, right? So the eigenvalue, sorry, the solution to that equation would be c1 e power lambda 1 t x1 plus blah 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 plus cn e power lambda n t xn. All right. All of this can be done, and it will be done again in the next class. So let's move on. But the most important thing is that linear equations and matrices do make sense, and they are extremely related to first order at least. I am not sure about second order. Differential equations is still an open topic. I don't think every second order matrix has been solved. Matrix equation, I mean. But first order, at least, it depends on the initial vector. It depends on the initial conditions. It depends on all the eigenvalues of the matrix. It depends on all the eigenvectors of the matrix. And it depends on the algebraic multiplicity. It depends on the geometric multiplicity. Right. So this is a quick example. We could breeze through it. And I mean, I wanted to remember that, like, even if you don't understand everything perfectly, this will be covered in the next class. So don't worry about it too much. You take du bar by dt equals some matrix times u bar. You want to find all the vectors u would satisfy this. You start with you're given that u of 0 is 974. So can you have any vector which transforms like this? You solve it the same way. You get the general solution, which is this. You plug in u of 0 in this. You get 2x1 bar plus 3x2 bar. You get C1, C2, C3 and C1, C2, C3. You get like three equations, three variables. So you solve for them and you get 2, 3, 1 as the coefficient, 2, 3, 4 as the coefficients. And the solution to this differential equation would be 2 e power t x1 bar plus 3 e power 2 t x2 bar plus 4 e power 3 t x3 bar, where x1 bar, x2 bar, x3 bar are these vectors. Right. But before that, I'd like to point out something. This is an upper triangular matrix, and upper triangular matrices in general are nice matrices. They can be diagonalized easily. Their determinant is simply the product of the diagonal elements. I think even their eigenvalues are these themselves. And these upper triangular matrices form part of the motivation for the Jordan canonical form, because that form was inspired by this. If you notice, if I put all these elements as 0 and I write the equation, determinant of this equals this minus lambda equals 0, I basically get 1 minus lambda, 2 minus lambda, 3 minus lambda equals 0, which implies automatically that 1, 2, 3 are the eigen values, right? So another interesting thing is, if they ask you if two matrices are similar and have an upper triangular matrix like this, you can basically look at the eigenvalues of these and just check whether they map with the eigenvalues of the original matrix. And if they do, then automatically it means that they are of similar matrices, right? So a matrix can also be converted to an upper triangular matrix by will, like if you want, whenever you want. And Jordan canonical form is an upper triangular matrix. So even if a matrix is not diagonalizable, it can be converted to an upper triangular matrix. Right. So let's revisit, like let's go to the previous thing. So we have du by dt equals lambda u, where u is a number. The solution is c e power lambda t. Again, I've made a mistake here, but please excuse me for that. And I wanted to notice the fact that it is a constant times e power exponential. Right. There's a constant term, and exponential term contains all the time varyingness. Now, if I look at this equation, right, du bar by dt equals a u bar. The solution to this is not of the exact same form. I want to have just a constant term times e power something times t, where e power something times t contains all the time varyingness. So how do I do that? And the way you do this historically, it relied on some very important observations by a lot of mathematicians. A lot of work into differential equations were done, and it was done by a lot of mathematicians. It wasn't the work of any single person, but this is where the fundamental concept of this e power a matrix times t times u of 0 came. Right. Now, I'm saying it depended on the work of a lot of mathematicians, because this was around the time, like around this time, even before this, even Taylor series came into existence, and you could write an exponential function or a sinusoidal function exactly as the limit of an infinite sum of polynomials. Analysis was being done. So this is another reason why you need real analysis, because real numbers analysis in general. Real numbers are easier to work with, but what about complicated objects like matrices? You would need a strong analytical thing to be sure that you're correct, to propose stronger properties. So yeah, this form has a lot of history behind it. And the form, let's look at the form now. It is e power at, a is a matrix, times u bar of 0. Now u bar of 0 bar is quite obvious, because if I put t equals 0, e power 0. I mean, I'm not saying e power 0 matrix, we're not clear on what that means, but in a way, e power 0 should give you 1 or the identity matrix, right? So 1 times u of 0, in a way, that would give u of 0 itself. So I don't think we should have any problem with the u bar of 0 part, but the e bar a bar t part is a big problem. What do we even mean by that? Right. And Yeah. Uh, we want something of this form. So some mathematician boldly hypothesized this thing. E power 80 as such is not a good thing because we don't know exponentiation well enough. In matrices at least because we haven't defined it. Now, before defining something completely new, let's look at what we already know, addition and multiplication. As I told you before, around this time, Taylor series was gradually growing in prominence. So some person put two and two together and was like, okay, a Taylor series, you convert something non-trivial like an e power something, exactly for real numbers, of course, into the limit of some polynomial sequence. And what is a polynomial? You have addition, scalar multiplication, and repeated like matrix multiplication. If I were to take unlock, right? So now, yeah, let's try the Taylor series for the matrix. For e power x. So e power x equals 1 plus x plus half x squared plus 1 by 6 x cube plus so on. Right. Now I want to convert this to e power matrix. Right. So how would I do that? So everywhere that I have a number, I would replace that by a matrix. That is the goal I have in mind. I have a number 1. I replace it by the matrix I, the unitary matrix. I have a matrix, I have a number x. X is a variable and in this case, it will turn out to be A. Okay. Till now, no problem. Now I have a number half. What do I do it by? I replace it by the matrix I by 2. Where it is like 1 by 2, every element is half. It is a diagonal matrix with every element as half. X square becomes A square. Now, is there any problem yet? No. I have a homogeneous equation of matrices. I multiply matrices with matrices. I define it only for square matrices. I do not want to define it for n cross m matrices yet because I do not know how that would behave. For square matrices, I can perform like squaring itself, cubing itself, raising itself to the power of n. I can perform addition of two square matrices, any two square matrices of the same order. So this substitution works. I think I've managed to convince you people enough. So that's exactly what's explained. E power 80 equals I plus 80 plus half. Now notice I could have written this as I by 2 itself because I times a matrix is the same as a matrix itself, but it doesn't really matter because that I is redundant in reality. So it is I plus 80 plus half 80 square plus 1 by 6 80 cube plus so on. The I here is to make the order 3, else you'd have a constant alone. And let's look at the properties of these, right? We define it in a way, and does it really behave in the same way as an e power kt function will do? Do the properties that we apply, so we just apply, right? We don't think about it. Whether it actually is correct. Does that apply for matrices? So e power 80, what is the derivative of that? A e power 80. Now, if I were to take this expansion, now I haven't proven that this expansion is yet correct, and I won't because knowing the expansion is important, but proving it is useful. It helps you, it gives you greater insight, but it is not essential. So if you want, you can look up the proof later. But yeah, if I were to differentiate this, the LHS would be d by dt of e power 80. I is a constant, so that would become 0. A is a constant matrix. So A times T would become A. It would become uh, A times T. It would become A square times T square. So every term in this would be multiplied by an A. So it will be A plus A square T plus half A cube T square plus 1 by 6 A power 4 T cube and so on. So it would be A times e power 80. If it were a constant e power 2t, differentiation of that is 2 e power 2t. So it is I mean, in general, it is very nice to know that the property still holds. Right. So what are the eigenvalues of this matrix? E power 80 is a matrix, remember. It's not a number. What would be the eigenvalues of this matrix? Right. So the way you do this is you look at this equation again. Now let me assume for the time being that an eigenvector exists, x bar. Let me or even before assuming that, I know a bar times x bar will give you lambda a bar times x bar. So let me just multiply both sides of this equation by x bar. Right? So e power 80 times x bar equals x bar plus ax bar plus half a square t square x bar plus blah blah blah, which gives you need to look at this carefully. So I becomes x bar, 80 x bar becomes t times lambda times x bar. I'll take the x bar outside for now. Okay. So let me just throw that away. So let's go from the first. I becomes 1. At becomes lambda. A square t square by 2 becomes lambda square by 2. This becomes lambda cube by 6. And so on. If I were to add all of these, I would get the expression for e power lambda t, right? So I would basically get e power lambda t times x bar. E power a bar t times x bar equals e power lambda t x bar. Right. Therefore, x bar is an eigenvector. If I were to apply the matrix e power a bar t on the vector x bar, I get a scaled form of x bar, right? So that would automatically imply it's an eigenvector, and lambda is still an e power lambda t now is an eigenvalue. So that is quite interesting. And if if a bar itself is diagonalizable, then e power a bar t is also diagonalizable. If it's diagonalizable, we can do a whole lot of stuff. So we can describe everything related to the matrix. Similarly, we have other properties such as e power at times e power bt equals e power a plus b times t. And the way you prove that is also similar. E power at the whole square would be e power 2at. I think that also holds. Right. So now for the diagonalization of this matrix. So yeah, in order to show e power 80 the whole square equals e power 280, this is what we will do. You know the eigenvector matrix, you know the value matrix. E power lambda t is eigenvalue matrix. So like just look at how we cover diagonalization and now it comes into play. Right? A lot of things went into this one discovery. So you have this diagonalized form. You apply this thing everywhere. E power a bar t equals I plus. So I'm writing a, I'm writing x lambda x inverse. So I'm writing x square, I'm writing x lambda x inverse times x lambda x inverse, and so on. So I basically get x bar I plus capital lambda t plus half lambda t square plus so on x inverse, and this simplifies to e power lambda t. So I would write e power lambda t using this kind of notation, I'd get the same thing. Alright, so now we have a diagonalized form. E power 80 whole square is e power 80 times e power 80. So that would be x e power lambda t x inverse times e power lambda t x inverse. E power lambda t times e power lambda t. You will find out that it's e power 2 lambda t. And that's how it works. Right. So some more properties. Till now we've been getting a lot of interesting properties. Interesting because they are what we expect them to be. I mean, I remember a quote from Einstein. The most strange thing about the universe is that we can actually predict whatever happens in the universe to a certain extent, right? So even in matrices, it need not happen this way, but for some reason, it's just very nice. So yeah, first property e power 80 always has the inverse e power minus 80. E power 80 times e power minus 80 is I, right? So instead of, I mean, e power lambda t times e power minus lambda t is 1. Similarly, e power at times e power minus at is I. The eigenvalues of e power a bar t is always e power lambda t. We saw that. When a bar is antisymmetric, e power a bar t is orthogonal. So the proof is given. Antisymmetric is when A transpose is minus A, and orthogonal is A transpose is I. So use the definitions to prove that. The inverse is e power minus at. The transpose is will turn out to be e power at the whole transpose. So the transpose goes to the numerator. A transpose is minus A because it's antisymmetric. So it is equal to the inverse. So you get inverse is transpose, and so e power a bar t is orthogonal. Right. So those are some properties. Uh, yeah, I guess that's all we have in the slides. But one or two more things in general about E-bar matrix is its utility mainly in covering the differential equation part, because right now for first order it's extremely useful, but in the second order it will turn out I mean a tad bit more useful, because these kind of generalizations aren't always possible, because like this, yeah, e bar lambda t times x bar, e bar lambda t times u bar of 0. One thing that you should probably do is to verify that these two solutions are the same. One solution we saw was e power lambda t u of 0. Another was u of 0 times e power at.
Welcome to.
So you're basically writing an infinite series, and you're writing an infinite series, you're summing that up and it turns out to be equal. So one thing that you could do to verify is do that. Apart from that, there is nothing, because these things are mainly used in differential equations. Yeah. So I think that concludes our session for today. We can like spend some 10 minutes to discuss doubts, if any. If you people have any doubts in the chat, like just type them in the chat box in YouTube, and I'll do my best to answer them. Are there any doubt? Like just tell me. Fine, okay. I guess in that case we can wind up with the session. Do you want to share another attendance sheet, like, or is it fine? Adria? Fine, okay. In that case, thank you guys. Hope you had a fun time. Yeah, have fun, I guess. We'll catch up later. Thank you.